Are we all sweet? With the recording and everything? Okay, awesome. Okay, so... Okay, cool. Good. Okay, awesome. Hi guys. I hope everyone's doing well. I hope everyone's keen to get down to some classical mechanics and special rel. I'm Anna, and you would have seen me in your lectures. And I am in your lectures. I'm currently taking the course, and that means I'm not an expert in classical mechanics or special relativity. The only thing I did to prepare for this revision session was attempt 2 of the past papers and then send my solutions to James for checking. He hasn't responded back to me, so I haven't verified these solutions. So you guys might need to help me a little bit, but we will get through it together. And I will post my verified solutions on the Discord after James responds to me. So get ready for that. Be on the lookout for that. But let's just get right into it because we're already 15 minutes into the session. The paper that I'm going to go through is the 2023 paper. And a little background on this paper, Adam Mikulich wrote the first half, and I'm pretty sure it was Oleg who wrote the second half. So yeah, I'm going to be honest, the very last question, the special relativity question, I think it's really easy, but I could have made a massive error. So we'll see how it goes. Let me just get to the paper. Is this the one that I wanted to do actually? Yes, it is. Okay. Can everyone get up the paper? Because I can't, it's a bit hard for me to show the question and do the working. So if everyone could get the paper up, that'd be awesome. I'm just going to go ahead and start off with question 1. And question 1 is the bungee jumping question. So it's a Mikulich question, so he likes to put in a lot of context. He says, basically, treat the bungee jump as an elastic pendulum, as shown below. The person has a mass m, and they're attached to an elastic spring of stiffness k. And when it's unstretched, it's at length L0. We can assume that all motion takes place in a single vertical frame. Awesome, love it. The first question is briefly explain the expected motion in this system given the 2 degrees of freedom r and theta shown above. So it's only worth 1 mark. So I'm just gonna, I hope this works out for me. I don't want that, I want this. Sorry, what paper is this again? 2023, sorry, 2023. I want a pen. I hope that's a pen. Yeah, okay, awesome. How do I change the thickness? Here we go. Far too small. You guys can read that all fine, I hope. Let's start off with question 1A. So all I said for this one is I described the types of degrees of freedom. So I said angular for one of them, obviously. And this is our spring. Uh-oh. Oh no. Uh-oh, no. Okay, spring, I've got to be careful, oscillates like a pendulum. And then the other one is the translational motion. And that's the simple harmonic motion of the spring. Again, I haven't had this verified by James, and also Mikulich is overseas, and I don't think he's easily contactable. So we're just gonna have to go with this for now. If anyone would like to disagree, please feel free. Moving on to part B, this is a 4-marker. It says obtain the expressions for kinetic and potential energies for the system once the system has reached a point where the cable remains taut for all motions of the bungee jumper thereafter. Ignore free fall components. So I feel like that was basically a pretty much convoluted way of saying find the kinetic and potential energy. For the potential energy, Tully. For the kinetic energy, I get this expression. Oh, that's a 2. Let me know if someone disagrees. Oh my gosh. Let me know if someone disagrees and we can go through how we actually obtain it. Are we all happy with that? And then all I do is simplify just a little bit. These extra little dots are going to be really annoying, but I don't know how to fix it. Okay. And I actually just made a mistake. Okay, cool. Sorry? That's R dot squared.
So the second line, yeah, like in front of the theta dot, that makes it squared.
Yes, it does. My bad. Good point out. Awesome. Are we all chill with that? I feel like that's a pretty common example, and that's therefore a pretty common kinetic energy. For the potential, I get this. So it's just the spring potential. And then also gravitational potential. Okay. Hopefully we're all sweet with that. Is this gonna... Cool. And I assume that the 2 marks for each of these will just come from correctly getting the kinetic and potential. As we'll see, Adam's questions get a little bit weird just because he gets you to explain a lot of things. So it's hard to actually see where the marks come from. Again, I can't ask him, but I will ask James eventually, hopefully, if he gets back to me. Going on to part C, it's just a simple show the Lagrangian is equal to something. So as we know, the Lagrangian is T minus U. And then if we plug that all in, you end up getting, I'm so sorry, I don't know how these dots keep appearing, but they just do. And it's going to be hella annoying, but we're just going to have to deal. It goes to this. So literally just doing T minus U. That one was only worth 1 mark for kind of obvious reasons. Part D was use the Lagrangian to obtain the equations of motions for the system. Hopefully everyone remembers this. We just need to do our Lagrangian, Euler-Lagrange equation in all of our degrees of freedom. So for the first one, it's just a really simple, this bad boy. So my first one is with respect to R. That's the first one I'm doing. Do you guys want me to actually go through and do all the derivatives, or are you guys okay if I just write the final result? What are we feeling? Sorry? Speed run through everything or final result? Write down everything? Okay. So on the left-hand side, this is what I get. I might just write down the initial thing and then go down to the final.
How's this being uploaded?
Onto Discord. The solutions will go onto Discord, and then this will be on YouTube.
Yeah, this is YouTube.
Yep. Continuing on, sorry. So this times 2 minus L. So that's what we do when we do our first run through of the differentiation. I'll just write down the very last step. Or actually, I'll do this and then I'll write down the last step. So this will just become M on, that's actually not going to become anything because the 2's will cancel. That'll just become M R dot dot. And then once we do all of the simplification, a bunch of these 2's will start to cancel out. And then a couple of things will simplify. And then I always like writing my equations of motion as a differential equation that's homogeneous. So the thing that I get at the end is R dot dot minus theta dot squared minus K on M of R minus K L naught minus M G cos theta is equal to 0. And then it's really clear what my acceleration factor is, what my R term is, and then the constant. Now, wait, sorry, Davide, do you know how to like stop these dots from coming? Because they're actually low-key very annoying. There's like dots that keep coming up every now and then. I'm now going to do the exact same thing, but for my second variable, which is my theta variable. Okay, no worries then. I'll just deal. Sorry? Okay. Basically, from this, we get mgr sine theta is equal to d dt of m onto r squared times 2 theta dot. And then this gives me theta dot dot minus g on r sine theta is equal to 0. Cool. This is where it gets kind of funky, and I don't think that Jan specifically told us what this was. At the same time, it was a super long time ago, so I actually don't remember. The question reads out verbatim, using a Legendre transform and starting from Lagrangian, obtain an expression for the Hamiltonian H in terms of the relevant generalized coordinate and momentum. In terms of relevant generalized coordinate and momentum, for Hamiltonian obtain. For the Hamiltonian you obtain, does H equal T plus V? Why or why not? Let's just start off with generalized momentum. So this is E. Yes. Starting off with my generalized momentum with respect to R, I get this bad boy. And if I do my Lagrangian derivative from before, we'll find that this is the exact same as mr dot. Yes. And then I'll do the other one on the other side. So the generalized momentum with respect to theta is going to be this guy. And that's going to be equal to mr squared theta dot. Awesome. And now this is like the Legendre transform. So it's H is equal to the sum over I for Pi Qi minus our Lagrangian. So if I'm just going to expand that out because I always kind of have trouble doing sums like this in my head. I'm going to get this minus my Lagrangian. Awesome. I'm just going to write this out super quickly. This will stay the same. And then my QR dot is literally just R dot plus, let me get rid of these dots, sorry. Plus P theta dot minus L. And then substituting in my PR and my P theta, my rho R rho theta, I get mr dot R dot, plus mr squared theta dot times theta dot, and then minus my Lagrangian. I'll just write the whole thing out so we have it. So minus my whole Lagrangian, which was, it's going to be m. Oh, no. Okay. It's going to be m onto r dot squared plus m onto r squared theta dot squared minus my k onto r minus L naught squared plus mg r cos theta. There we go. And then after some simplification, I get the following. So I'll just write everything out. So just in case I make a mistake. Ooh. Okay. And then what I do is I write my like simplified expression in terms of my rho r and my rho theta. And when I do that, I get the following. I get rho r squared on 2m plus rho theta squared on 2m r squared. And they literally correspond to these first two terms. And then I get my plus k onto r minus L naught squared minus mg r cos theta. And basically what we can say, or what we can see, is that, can I do highlighter? No, that's fine. So this first term is my radial kinetic energy, and this second term is my angular kinetic energy. This term is my elastic potential, and this, of course, is my gravitational potential. So we have our kinetic and our potential. And then if you go back and compare the terms with the Lagrangian from before, you'll realize, so remember how we started this? We started this off by saying that H is equal to the sum over I of Pi Qi dot. And by comparing, you will actually see that this is equal to T plus U. So therefore, it is equal to the sum of the energies of the system. It also did ask, or is that the next question? Sorry, hang on. Oh, no, sorry. It does ask for the Hamilton you obtain, does H equal T plus V? So it does. And if you guys remember from the revision session that Jan ran in his first half, he said that it was because there are no time-dependent coordinate systems that we're using, which means, Tully, can you just correct me if I'm wrong, there's no energy leakage or entering into the system. Yeah, exactly. Yes. Does that make sense to everyone? Cool, cool, cool. Question, or part E rather, says, we just did that, lol. Question F, sorry. It says use Hamilton's equations to obtain the equations for motion for this system. And then do you obtain the same answer as for D when we use the Lagrangian? If so, why not? So this is F. So starting off with my Hamiltonian that I had before, in terms of my generalized P's, I have this one again. And then hopefully you remember that we have this equation with respect to Pi, and then Pi dot is equal to the negative of this with respect to this. If we go ahead and do the first one, so the first one that I do is my PR, or my rho R, is equal to this one. Whoa. Whoa. dr. If I go ahead and do that, this is the result that I obtain. So I write it all out super simply so that I don't make a mistake, because I feel like in classical there is a lot of algebra, and even though it might be easy, it definitely is really, really easy to make like a little forget the minus sign kind of error. Oh, sorry. Oh my gosh. Oh my God. And then after I do all of that, what I want to remember is that my rho R and my rho theta are actually functions of R and theta. So I literally write out the same thing again, but replacing my, oh my goodness. It really is no joke. If anyone had Shushkov this year and remember how much he used to complain about this vibe, like, it's totally valid, 100% valid. It's actually so annoying. Okay, so I'm just rewriting my rho R and my rho theta because they are dependent. Oh my gosh, they are dependent on R and theta, and then this just stays the same. Oh my gosh. Okay, if I just go through and do that now, my first term is not dependent on R at all, so that after the differentiation will go to 0. What you do end up getting is, oh my goodness, I'm actually going to lose my mind. Okay. What you end up getting is, I hate these stupid dots. Okay, is this guy. And then after some simplification, you end up getting this. So I'm literally just going to divide everything through by m. GR cos theta. Awesome. So that's my first equation of motion. And then if I do the exact same thing, but for my other Hamilton equation, I get this guy.
Like just a question. Right?
Yeah.
Can I set a Lagrangian for R? Oh, okay, so that was positive. Yeah. So I didn't do it well.
Okay. If we go through and do that, again, I'm just going to write out my PR and my rho R and my rho theta in what they actually mean, because they do have an R and a theta dependence. Oh my goodness. Okay, and then after I do all of that, I end up getting to, there's a bunch of cancellations that happen. In this case, also, it's probably good to note that this one becomes 0 because there's no theta dependence. After we do all that simplification, we get theta double dot is equal to negative g on r sine theta. This potentially could have been a plus because I think I missed the minus. So potentially could have been a plus. It is meant to be a minus. I have it in my notes actually. So in my solutions, I have my Lagrangian written out again, and our theta double dot matches up. But let me just look at my R double dot. The R double dot doesn't match up. And I don't have a good explanation for it. Where my Hamiltonian is different from my Lagrangian is the R double dot is fine, and then this term has a negative sign or a positive sign that should be negative there. Say that one more time, sorry.
So the K on M is fine because that actually goes to negative. There's a minus
Yep.
in front of the bracket. Mm-hmm. The R x dot squared up front also becomes negative, but it should be positive. That makes sense. So in the Lagrangian, that R double dot, that R dot squared is positive, and Hamiltonian is negative.
Yes.
So I would make a map error.
Yes. Because I don't think here there are time-dependent coordinates. Speaking of though, Jan did say that we should be able to quickly identify time-dependent and time-independent coordinate frames. I'm going to be honest, I can't do that easily. Can anyone else? And does anyone else have any input therefore? Sorry? Yeah, I know it doesn't here, but like I haven't seen in this course an example where it does. I only have seen on the internet that sometimes the Hamiltonian is not the sum of the kinetic and potential, but it still kind of baffles me sometimes a little bit, especially because they're supposed to be all equivalent, Lagrangian, Hamiltonian, and Newtonian. So I will look through my solutions before I post them up, and I hopefully James also can maybe spot where the error is. But they should be the same. And note again to what Jan said this morning and Oleg, we did expect them to be the same. So if we find that they're not, we can just write a little note and hopefully that negates a mistake and we still get a mark. But moving on to, so that's the end of the first question. And that question was basically copy pasted through all the past papers that we have. The scenarios are just completely different, but it's the exact same questions kind of. Moving on to question 2. Again, Adam Mikulich context. So it says, one of the joys of outback driving is the washboard road. What is G? Oh, is G just plugging in values? Do you guys really want me to plug in values? You guys can plug in values yourselves. Maybe I missed it. Oh, that would have been awkward. Victoria. It's just like rearranging equations and plugging in numbers, isn't it?
Because you're at max length, which you know is at theta naught, right? So
yeah.
Makes assumption theta 0.
Yeah.
Also, because it's the maximum, you make the second time derivative equal 0.
Yeah.
But for the first time derivative, just have this kind of term sitting out there.
Mm-hmm.
And at least my solution is more manual approximation at that instant.
And
you kind of just ignored it, but I don't know if that was.
Yeah.
Why did we find out? Like the variables.
I have a feeling it's because he wants you to use the constraints in the setup of the problem, so the taut rope and all of that. And then also you have to do this cute little thing where you have to sub in a mass without getting given a number for the mass. It's a classic Adam Mikulich thing to do to like actually make an estimation. I'm pretty sure in quantum when I did it, he gave us an example of like always just saying a human was 50 kilos and you just always subbed in m is equal to 50 kg. So yeah, that's what I think at least. I didn't ask Mikulich actually because I can't get into contact with him, but yeah, I also kind of doubt that Jan is going to make us start plugging and playing because like it's more efficient to test like the actual fundamental skills of Lagrangian and all that stuff. All this other stuff is just like, can you do some algebra? Which like, hopefully they would have tested in first year, right?
So for this question, we probably also just use the fact that H equals T plus B. So energy is conserved. You start with the certain gravitational potential energy. So then you can work out the time when your kinetic energy is 0. That gives you an expression for the distance from L to 0.
Yeah. But going back to now question 2. So you've got like a washboard road in the outback, and it's periodic ripples that develop in the surface of an unsealed gravel or dirt road due to the suspension system of cars passing over the road. So small ripples cause the car to bounce as it travels, which leads to more ripples for the next car and so on. A simple model for a car has the car body resting on 4 springs, 2 at the front and 2 at the rear. The 2 front springs rest on the front axle, which drives the front 2 wheels. The rear 2 springs rest on the rear axle, which drives the rear 2 wheels. Each axle assembly, i.e. axle plus 2 wheels, has a total mass of 50 kgs. The worst speed to drive at is one where the periodic driving from the ripples is resonant with the suspension system. Question 1 is, if 4 passengers each weighing 80 kilos are seated in the car's body lowers by 2 centimeters. What is the spring constant K for each of the 4 springs? So the thing that I used, classic Newton. Oh my goodness. Classic Newtonian approach. Literally just saying that the displacement in the spring is caused by the mass of the people, which looks like mg is equal to kx. And then after you apply, so you put in, I did 80 times 40 for the mass, 80 times 4 for the mass, G 9.8, and then 4K is equal to 0.02 because each spring is going down by 2 centimeters. And the thing that I get is K is equal to 39200 Newton meters. And then I feel like this is a massive spring constant. But at the same time, exactly, it's a car. So I thought that it was a reasonable answer. Does everyone else think it's a reasonable answer? Okay, awesome. That's right. Yeah, like you don't want it you don't want it bouncing around. Oh, really? Potentially. Potentially, yes. There's one on each wheel. Yeah, and I did say 4K. Awesome. Part 2 says, given the information about the axle assembly, what is the natural resonance frequency of the axle assembly oscillating on its 2 springs? It gives us a hint to think carefully about what happens to K. So this is part II. Hopefully you guys know this. I'm pretty sure this is also on the formula sheet that they give us, is that the resonant frequency, these dots are really going to bug me, is the square root of K on M. I'm just going to consider one axle assembly, which means the mass is 50 kilos and it has 2 springs with the K that we did before. So I said that this was equal to 2 times the K that we got before. And I also made sure that everything was in SI just because I don't want to do conversions later. And I get a W or an omega of 39.598. And this is in rads per second. This is like a tiny little thing that I always do. It did ask for a frequency and not for a omega. So I just convert it to hertz. And I get this.
Oh, is this mass not including the passengers? Yeah.
Yes, that is correct. In which case, I'd have to add 160 because hang on, how heavy are the passengers again? 80 kilos. So yeah, 160. They're not 50. In which case, these answers are. Oh, I didn't consider that. Does the weight of the axle have any effect on the spring? The springs are on top of the axle. Is that how suspension works? I actually have no idea. But the wheels are touching the ground, the axle is not on the ground. Where is the axle with respect to the spring?
So you have an oscillator, if you have a single like K attached to a mass, it's the same as having 2 masses on each side. Like one on each side is the same.
True that. So in that case, is this answer valid? I actually did not think about that when I initially did this problem.
I don't know. I think this guy's driving it. I'll take one.
I will potentially ask. I'll make a note. I will look into it. So the issue is that
It doesn't matter. This is like trivial part of the question.
Yeah, just by explaining. I will actually look into that because that is, yeah, interesting. Okay. But like, do you think they were just throwing the mass as like a red herring? The third part of the question is, if the adjacent maxima for the road corrugation are spaced by 80 centimeters, what is the speed of the car where the resonance occurs? Yeah.
I swear if I lose a mark, I don't know how suspension.
Yeah, yeah. I really don't feel like, because that's not even testing like, do you know how to do classical? It's like, do you know how a car suspension works? Are we okay to just move on? Because I actually don't have a better answer for you guys. I'm sorry. I remember I'm not an expert by any means. By any means. Oh my goodness, yes. Don't even get me started on admin solutions. Okay, part 3, sorry. So this one is a cheeky little one. So this is what I drew, just like 2 things. And I'm measuring this as 0.8 meters. And then I use everyone's favorite equation, this one. And we just calculated the frequency. I'm just going to use what I miscalculated before. But essentially, once I chuck that in, I know that my wavelength is 0.8, and I want to find my velocity. I end up getting a velocity of 5.04 meters per second. And I feel like that's kind of reasonable, because if you were to drive slowly over the bumps, it would be really bumpy. But if you were to like zoom past, right, you wouldn't be as bumpy, you'd just be flying over all the ridges. So I felt like that kind of made sense. And if everyone agrees, I'll just move on to part 4.
Don't worry about it.
Stop it. Anyway. So this is a question that I kind of like, I didn't know. I feel like this question would have been easier if I had seen Adam's notes, because when I did it with our notes, I like waved my hands a little bit and I'm like, okay, this is the result, without actually proving it. It's also worth 5 marks. So I thought that like I would at least need to do a little bit of maths/derivation in order to get the marks. So what I start off with is I start off with just Hooke's law. And we also want the minimum damping coefficient. You get the minimum damping coefficient when there's no resonance, or we have an overdamped or a critically damped solution. So if you guys remember that, you have regularly some oscillations and maybe they're damped and they go to 0. A critically damped would just be like this one. That's kind of dodgy, but you get the idea. Sorry? So overdamped goes straight down. It doesn't even get to 1 oscillation. Is overdamped. Critically damped is like the envelope. I'll do some maths and then hopefully that comes out. So but I want the critical value. So I want the red line. I start off by considering Hooke's law, and this is just like straight up from the notes. So kind of like the method that we use in the notes. So I start off with Hooke's law. Love it, classic. And then I add a damping constant. And I remember Adam said this at the very beginning of the course as well. Typically our friction or our air resistance or any kind of damping is always a function of the velocity. So I add like a velocity term. So I end up getting that my mx double dot is equal to negative kx plus, or in this case minus, a bx dot. You could do a plus, in which case if you wanted to calculate b, it would be a minus. So it's completely arbitrary what we choose. If I then just isolate or bring everything to one side and make this monic, I get this expression. And then this is something I straight up get from the lecture notes. We then re-express this differential equation as this. Where, no, it's in a different color, 2 beta is obviously equal to b on m, and omega naught is equal to root k on m. That's something that Jan straight up wrote in the notes, so I just copied it down in this little derivation. We then need to use an ansatz, and my ansatz that I'm going to use is the classic. So this is going to be a function of time, and I'm going to make it this, in which case my x dot of t is equal to re to the rt, and my x double dot of t is equal to r squared e to the rt. When I substitute all of that in, I'm going to get a quadratic equation. And that quadratic equation is going to look like this. No, that's not right what it is. Ooh. This is what it is. And then when I solve for r, I'm going to get this guy. And this is still like straight up from the notes. And that gives me this. Awesome. And again, this differential equation was just like the most general kind of oscillating. We then, in order to get our conditions for underdamped, overdamped, critically damped, start playing around with these constants beta and omega. So if I just write down my general solution for my oscillating or my oscillator, I'll get this. And then I'll get b squared minus omega naught t. That t is outside of the square root. And then I'll get the negative version. And maybe I'll just like make it super clear. And then I say for critical damping, so critical. For critical damping, I need this condition to be in place. And if I compare that to the resonant frequency that I got before, omega naught is the resonant frequency, I end up getting a beta that's equal to 6.3022. Yeah, and that's basically it. Hang on, let me just, yes. There is a problem in this question that I kind of found in our notes. So I just used like the most simple derivation that we use in our notes and then imposed the condition. In our notes, Jan also wrote out without proving that the general solution for a critically damped oscillating system, it has a general solution that is this. So it's going to be e to the b t outside of a e to the squared. Sorry, there's a squared in there for both of them. T, and then it's plus big B T e to the whatever. So, but he never like proved that. He just told us that, well, that's what it was. For this question, it was a 5-mark question. So like, do you guys see my problem? I don't know what to do here, if I'm being honest. Well, yes. So this is where like I don't really know.
From a differential equations course, the t comes when the roots to the characteristic equation are the same.
Okay, gotcha. Which does make sense as to why it's more general, that this is the general solution for a critically damped. Yeah, this one is only critically damped, whereas the one I have up here is for a general oscillating system with no condition. So again, if I were to write this in an exam, I'd write down this first derivation that I actually did and write down literally what was in the notes, and then I'd be like, there's like a discrepancy here and I don't actually know why. Was that differential equations course 2221? Okay, I haven't done that one yet. WAM booster? Yeah, okay, good. So yeah, does anyone have any input on that at all? Anything they'd like to add to that?
So you said before the other one was the general solution for oscillating.
Yep.
Which version was that?
That was this one. Oh, this one has a T in front of the B, yeah.
Okay, thank you.
That's all good. Going on, I'm not going to write this one down because it is a lot of writing. I'll just kind of describe it. It will be in my solutions though. So for part B, it says briefly explain how a playground swing works. Is this still the right question, lol? Am I? What? Okay, it says briefly explain how a playground swing works. Is this the right paper I'm talking about still?
Briefly explain how a playground swing.
Okay, so it's not the bub swing, mum swing question. Okay. In your answer, you should address the natural frequency, driving oscillation, and how it's achieved, what the phase of the driving oscillation relative to the oscillation of the swing needs to be. If it helps to draw a graph to answer your question or answer the question, please feel free, but it's not essential. So I said natural frequency is determined by our 1 on 2 pi root g on L. That is just like a pendulum natural frequency equation that like we proved in first year. For the second part, the driving oscillation is typically achieved by someone pushing the swing. It's like, you know how a mum or a dad will stand behind their kid and push them. That's our driving frequency. This continuously adds energy to the system. So obviously if you push a child on a swing, they'll get higher and higher without doing anything. And then for the third part, for the phase, I said in order to have the most effective energy transfer, the driving force needs to be applied in phase with respect to the natural oscillation of the swing. So when the child is at like the stationary at the top of its swing. And obviously that makes sense, right? Because they're starting from rest. It's like super hard to have an efficient energy transfer when they're right like at the lowest point of their swing, right? Because they're moving at maximum velocity. Then I say when this happens, the driving force and motion of the swing are in the same direction. If the driving force were out of phase, the swing would slow down and eventually stop oscillating. Are we all in agreement with that? Why are you? Ooh. Oh, you had legs. Yes. Yeah. I don't know if you guys have done the 2022 paper, but it talks about like mum swing and bub swing. Yeah, and so many words. So hopefully Jan doesn't do that to us. I did have Jan write the first half of my 1B paper, and it was just calculation, which was amazing. The second half did require more words, which kind of sucked. But that's okay. So I really don't think that Jan's gonna make us like apply this to real life. Hopefully not, at least. Part C goes, consider the scenario in B. Suppose at time t, the person riding the swing deliberately changes the phase of the driving oscillation by pi. What changes in the dynamics that follow this? Briefly discuss. It's only worth 2 marks. All I said is by changing the phase of the driving oscillation to pi, energy is continuously removed from the system, reducing its amplitude and eventually making the swing come to a complete stop. Do people agree, disagree, partially agree?
Would it start swinging again in the other way?
Eventually, and then go into the opposite direction? Yes, it would. Yeah, I should extend it. That's probably where the second mark comes from, actually. But I will all sweet with that. Awesome. Okay, this next question I feel like is the crux of the course. And I feel like undoubtedly it's going to be in the final. It's question 3. I'm just going to, and this is also the one that I've compared with the most amount of people, and we kind of get different results. So let's do this together, please. I'm just also going to have to draw this one up. So we have one swing and then okay, let me just do my setup that I did. Before I start this question, what do you guys reckon the 3G and the 1G mean? Hate it. Okay, that's okay. The first time I did this, I thought that it was like G's. So I was like, oh, 1 times 9.8, 3 times 9.8. which is really silly. Don't do that because then you only get one mode of oscillation, and hopefully you can kind of see that this will have two modes of oscillation. But what does that G mean to you? Mass, yeah, right. Yes. Yeah, tell me. No, but my notes have this. My notes have this, and all the other constant stuff just disappears eventually. So like, it's chill. It's chill. It's chill. Relax, relax. The first part, if the block has mass 1g and it's slightly displaced from its equilibrium, assuming that the oscillations are small, write down the full Lagrangian of the system in terms of the physical parameters and coordinates. Actually, if we do choose a different coordinate system, I don't have the solutions in that coordinate system. Will you guys help me?
The solutions you had were in the coordinate. Like if you do this one where you measure baseline, you also got to have a constant LO.
Yes, yes, yes. But that just goes away everywhere.
I know exactly.
Do you guys want to take the origin from being up here or from equilibrium? What are we feeling? I have 2v1 from the top. Yeah, right. I don't know. Tell me about it. Or is the equilibrium not moving and everything else moving? Did the apple fall on Newton, or did Newton fall onto the apple? Like seriously, let's be real. Let's be so real. Did the apple fall on Newton, or did Earth and Newton move up to hit the apple? Like exactly. Yeah, as Shushkov would say, it's just semantics. Semantics. Anyway, I'm going to choose my fixed thing as my reference point. Feel free to do whatever you like, though. This is just what I'm going to do. So we want to write down the full Lagrangian for my potential energy. I get 1/2 m1 x1 dot squared plus 1/2 m2 x2 dot squared. For my U, I get 1/2. I'm just going to straight away assume that my K's are 1, 1, and 2. So I'm going to get, where is it? I'm going to get 1/2 x1 squared plus 1/2 x2 squared plus x2 minus x1 squared. And I got no constant out the front of the x2 minus x1 because kc is equal to 2. 2 times 1/2 is 1. My Lagrangian then becomes 1/2 m1 x1 dot squared plus 1/2 m2 x2 dot squared minus 1/2 x1 squared minus 1/2 x2 squared minus x2 minus x1 squared. Okay, cool. This is where I then sub in m1 is equal to, relax, g, and m2 is equal to 3g. And when I do that, I get this, 1/2 g x1 dot squared plus 3. Yes. Wait, what cancels anyway? If you were to include gravity. This g is not gravity, it's grams.
Bro, okay.
I'm so sorry. I'm so sorry, though. But I misinterpreted it wrong the first time. I misinterpreted it the first time.
Sorry.
No, please.
You got rid of the 2 at the front of the x2 minus x1. That was actually x. That was kb kc.
Oh.
The kc is at the front of the
Which one x2? I know, it would be half.
It would be half k2 minus k1 and x2 squared.
No.
Because it was, yeah. And get rid of the x2's one.
And it's still a minus. Okay. Where was I up to? Okay, so I have this one, and then that's a 2 as well. That's not really that clear. Minus 1/2 x1 squared minus x2 squared minus 1/2 x2 minus x1 squared. Okay, cool. Now I'm going to go ahead and do my Lagrangians. Is that still kind of easy to read? Maybe I need to zoom in. Awesome. Let me just do this now. So on the left-hand side, I'm going to get this term and this term. That's going to end up canceling, and I get this, and then I get plus x2 minus x1, and that's equal to d dt of, there's a dot there, that's kind of hard to see, and then this one will be just g x1 dot. Simplifying that, I get minus 2x1 plus x2 is equal to g x1 dot dot. I'll just do this one over here. And that's dx2 dot. Okay, cool. On the left-hand side, when I differentiate with respect to x2, I'm going to get a minus 2x2, and then I'm going to get minus 1, sorry, x2 minus x1, and then that's going to be equal to this, and that becomes 3 onto g. There was supposed to be a squared there, so that just becomes a 3. 3g x2 dot. And by rearranging, I get negative 3x2 plus x1 is equal to 3g x2 dot dot. Just to remind everyone, the g is for grams. The next thing that I do is, it's actually the next question. It's finding the normal modes and the normal coordinates and the associated eigenfrequencies. So there's like a million ways to do this, and by a million I mean like 3. I'm going to use the matrix equation just because I feel like that's the easiest for me, or the way that I find the simplest and the nicest. So I'm going to write out my equations that I just found in matrix form, and the matrix form is this. So hopefully you guys remember seeing this. I'll actually go through it because it's a revision session. Why not? In order to find out what I need to find, I'm going to substitute in these guys. That's a vector. And if I quickly, oh my gosh, if I quickly differentiate, I get I omega a e to the I omega t, and dot dot is equal to negative omega squared a e to the I omega t. If I substitute that into this equation and do some rearranging, I end up getting k minus omega squared m of a is equal to 0, which is like the most important part of this. I then need to find my eigenfrequencies, the determinant of k minus omega squared m. And I want to make that equal to 0 for my eigenfrequencies, or my eigenvalues, eigenvectors. When I do that, I might actually just need to look up here. Let me write down what my masses were. My mass matrix was G, 3G. Again, G is grams. Uh-oh. That's a 0. And that was my M. My K was 3, -2, -2, and 3. Let me just make sure that that's actually what I get. That's not what they should be. Well, oh, wait, that's wrong. That's from up here. Are we chill with that? What was your K then?
My bottom right is 1.
1.
Well, it's all negative, but it doesn't matter. Like, I might have put my sign in.
Andrew, what did you get? And Tully, what did you get?
The same as you just.
So I just put the negative somewhere.
Because I think
Yeah.
this is my
Yeah, different coordinate system. That's right. Yeah. Okay. Sweet. Okay. We'll just roll with this. Again, it's about demonstrating the skill, and then we can just comment on the reasonability of our result later. So when we sub this in, I'm going to actually have to do this. I need to get the determinant of my K is my -2 minus omega squared G. That's going to be just a 1. That's going to be just a 1. And this is going to be -3 minus omega squared 3G. I need to find that when it's 0. Determinant, so that's going to be equal to -2 minus omega squared G. -3 minus omega squared 3G. That'll be a -1 is equal to 0. Expanding this out, I'm going to get 6 minus 6G omega squared plus 3G omega squared plus 3G squared omega to the 4 minus 1 is equal to 0. This is just a quartic equation or a quadratic equation in omega squared. So I get this.
should be a 6 plus 6G.
Omega to the 4. Yeah.
In line up. You've got a minus in there.
Lol, yep, my bad. Yep. Okay. So that's a 9. Okay. Thank you. And then my constants make a 5. Okay, cool. So you get an omega squared, that's 9G plus or minus 81G squared minus 3G squared on 6G squared. Let's just go through and do the simplification. So that's going to be 81G squared, and then 20 times 3 is 60 minus 60G squared on 6G squared. 9G plus or minus. 81 minus 60 is 21, and 21 isn't a nice surd. So that's just going to be root 21G on 6G squared. I'll just write it out like this. So that'll be 3 on 2G plus or minus root 21 on 6G. And my different omegas are going to be the plus and minus version of that. Can someone really quickly, actually, I'll also do it. I'll just do it. It's okay. To get to the answers, you just need to put that into your calculator and then switch the G to a 0.001 because, again, we're in grams. When you do that, you'll get this. This is going to be so awkward if I get a solution that doesn't work. Oh, sorry, and these are both squareds. And then this one is awesome. I would find the omegas, but we'll actually need the omega squareds to find our equations up here. So I want to sub back into my, I'll write it down, sub into. So the point now, I want to sub back into this equation and I want to find my values for A1 and A2. Remember, this is a vector. When I do that, oh my God. Oleg moment. Oh my God. Oh my gosh. Okay. No, you don't even understand. Oleg's complaining is so valid. You don't even get it. Okay. Should I do this whole subbing in and the computation to find A1 and A2, or do you guys feel like you can solve a simultaneous equation? We can solve simultaneous equations. Is that a maybe? Is that, what does that face mean? Good. Everyone can solve simultaneous equations, and everyone knows what to do from here. Chill. Okay, cool. Oh, okay. In that case, okay, good. Okay, yep. Let's talk about the last question, and then we'll probably have time to chat about a couple of questions from 2022 that I wanted to go through. Okay, cool. So solve simultaneously, I'll just write. Oh my gosh. This makes me want to cry a little bit, I'm not going to lie. Where did it go? Oh my gosh. Okay. Question 4. This is, I feel like, incredibly simple, but at the same time, that makes me really worried. So we have a space shuttle that travels past Earth and Mars in a straight line at a speed of 0.6 c. At the time when Earth and Mars are 2.4 times 10 to the 11 meters apart, the distance is measured in a fixed frame of reference in which the Sun, Earth, and Mars are at rest. You can neglect any motion of the planets with respect to each other and the Sun during this short time. Question 1, in the fixed reference frame, how long does it take for the space shuttle to go from Earth to Mars? So it'd be like if I was completely stationary, the Sun and Earth and Mars are completely stationary. How long does it take for this thing to get from Earth to Mars? This is just like really simple, I hope. My Earth, my Mars, the distance between them is 2.4 times 10 to the 11. I just use velocity. Oh my goodness. Oh, I'm going to rip my hair out. I can't see it. Oh no. Okay, I'm just going to start again, I guess.
You think the button down the bottom next to the 3% plus? Left, the box with the arrows.
We usually know what the types of priority.
I'm just going to start this one again because I can't find it. No. Okay, so this is my Earth. Okay, for this question, I just use velocity is equal to displacement over time. Subbing everything in, 0.6 c is equal to my 2.4 times 10 to the 11 on time. And then you end up finding that time is equal to this seconds. And I feel like that's fairly reasonable because 2.4 is a massive number and 0.6 c is like pretty fast, but it's not like speed of light fast. You know what I mean? So I reckon that's a pretty reasonable result. For the second question, and this is where I might need help, it says, in the frame in which the space shuttle is at rest, how fast are the Earth and Mars moving? What do people think we need to do for this one? Okay, excellent. Excellent, beautiful. Does everyone agree with that? Because that's what I thought, but I was really scared that I was wrong. No disagreement. I love it. Okay, so therefore, V of Earth is equal to V of Mars is equal to negative 0.6 c. Love it. Okay, cool. This is where it starts to get like a tiny little bit saucy, but like it's really nothing too horrible. Part C is in the space shuttle frame, how far apart are the Earth and Mars? So you end up using length contraction, which is this guy. The formula sheet that they give us doesn't actually have any of the length contractions or the time dilation. So if you don't remember it, I guess like write it down. When I plug all my values in, I end up getting this, which is smaller than my initial 2.4 times 10 to the 11. So it makes sense. For IV, it says in the space shuttle frame, how much time elapses between the Earth passing by and Mars passing by. For this one, I just use the regular time dilation one. So easy at first, you could do it.
Yeah, this could be done default.
Yeah. I know, right? And I get 1667 seconds, which is longer than the original, which makes sense because you're traveling faster. And what's that thing that James always says? Moving fast means time goes slow. Tick slower. That's the one. That's the one. That's the one. Okay, awesome. And that's it for that exam, basically. Yeah. Sorry? Wait, what am I doing? Yes, Davide.
Question one, I think we're trying about the potential of the kind of brushed out is the potential of one minus scroll up to one.
Oh, I don't know if I can find that. Yep. Yep.
Would you take your L from part 3 divided by 0.6?
Take your L from point 3 and divide it by
0.66, because the distance is
this is a distance, right? And this is a V, and that should give you a time. Let me give that a go. So the length from there, 1.92 times 10 to the 11, and I divide that by 0.6, 3 times 10 to the 8. Okay, when you do that, you get a T of 1.066 times 10 to the negative 19. Wait, 1.92. Oh, it's times to the 11. My bad. That was me. That was me. That was me. That was me. That doesn't actually change anything. You still get a 1066. Sorry? So wait, you did, like, when you say Lorentz transform, do you mean this thing?
No. Stationary frame of Mars, event one.
Yeah. Yeah. Uh-huh.
I got to 1066. Because it doesn't make sense to both the length.
Let me just replug this in my calculator. So does everyone agree that the time it takes in the stationary frame is this 1333? Does everyone agree with that? I still get 166. Hmm. I know. I know. It makes me, I don't know. And I hate it when it doesn't work or when we get different things.
Did you use the same reasoning at right side?
No.
So what do you do? Well, once you got the length contraction, then you know the length and you know what speed they're going. How would you go negative? Because I feel like that's the reason why it's in this part 4 you've done. I don't think you're kind of length contraction because it happens simultaneously. At the same time, your time is dilating, length is contracting.
And I feel like that results in a shorter time because at the same time, time's going slower.
Yeah, yeah.
Like the distance to travel in a way is getting shorter for a certain distance.
Also, wait, what did you say again? So you consider the simultaneity thing. So are they start at the same place at the same time, and
So, yeah, amount one, which is x 0, t 0. Amount two is like b and x kind of plus one. We have like the velocity and the distance. You can say, just transform those using the frame of the sheet. I get that.
Okay, if you get the velocity equation for the frame of reference, you get the tractive length and the dilated time on the left, then you get different velocity. So it wouldn't make sense to use the same.
Also, I think so. I think if you instead of divide by 1 minus theta, or
Yeah.
divide by gamma equals times by gamma. I think because I think that works as well. That works as well.
doing T gamma, you mean?
Yeah, delta T gamma will give you your 1.066 point.
It's just that square root.
Oh, sorry.
Yeah.
Yeah. So multiply instead of divide. And so basically you want the time on the ship to be smaller because if you think about the muons traveling down,
Yeah.
they experience a small time. Compared to us, we see a big time. So I think it should be smaller.
The time,
The time.
in which case 1.066 does make more sense.
So if you get the 1066.67, you get 0.6. If you use the tractive length. So in my opinion, that makes sense.
Yes. Okay. In that case, I will get rid of this. And we just multiply. I will also change my initial solutions. Okay, cool. And then that's 1066.67 seconds, which makes sense. Okay, cool. Are we all sweet with that part then? Yep. Okay, Davide, what were you saying? I don't know if I'm going to be able to find it because I don't know what happened. No.
There's a few things we observed. One, the question itself said, is this the Lagrangian? Didn't have a dot above the R, which it just has to. So that's like a mistake on how to just.
Oh, yeah. It did have a typo. Yes.
There was one small thing detail, which is like we said, just gravity negative mgr cos theta. Small niche things that doesn't actually matter because it should be mgr 1 minus cos theta. Because the delta h, like your h variable, because your max r is r, like cos theta thing, that's to actually be minus that. Because otherwise it was just in the Lagrangian minus 1g cos theta when theta equals 0, the radius would be 0. But again, it doesn't matter if the constant term, it goes away. Because if they're saying right, the Lagrangian technically include that 1 minus cos theta, that is the Lagrangian.
Hang on. Wait. No, but it's still kind of important because it is.
So question 1, potential energy. If you remember the system, you can just write it out.
I have it literally right here in my solution, but I don't know where it is on the in here.
Maybe just go to page 2.
But then that just creates a new page.
Yeah.
Or,
You don't want to make it just right over. I guess what I'm worried about is if you zoom out too far.
Let me just write this on my solution. So wait, you think it's just the 1 minus cos theta?
Yeah.
Let me just understand real quick. I know, but still, semantics. Sometimes semantics are important.
Negative mgr cos theta plus the term.
Yeah.
It should be negative mgr 1 minus cos theta in a little bracket. The reason is theta equals 0, r, when we're changing the height, obviously this height is r cos theta. So we've got a minus from the r. So exactly 1.
It is.
So it doesn't have 0 value there.
It is.
Goes away.
Yep. My bad. My bad. That also is, yeah, I should have picked up on that. No. Yeah, I don't know. I like literally, I don't know. Is there a specific question from the 2022 paper that we want to talk about? Because I low-key want to talk about question 2. Question 1, sorry, question 1.
We had a debate. Degrees of freedom for the class. Did everyone do 2022? Someone do it? Yeah, exactly. Little ball on a track.
Yes.
These guys are saying it's only got 1 degree of freedom.
In the first part. Yeah.
But it is a sphere, right? Like
yeah. But like,
even though it's C, the sideways dimension, it doesn't mean it doesn't exist.
That's true, but we don't need to use the second degree to like store any information, right? It's okay, at least it's on the recording, and I have it here.
Just send them to me when you're done.
And when James verifies as well. James needs to verify still. Okay, how'd you get that? So how do you get 7? Okay, cool. So wait, let's just run through it. Guys, I've lost my pen. Oh, no, I have it. Peace out. Good luck. Okay. Expected dynamical behavior, the thing rolls down, or it doesn't roll down. It does roll down. Degrees of freedom. So how many degrees of freedom did you say there were? Okay, yeah, that's right, yep. Yeah. I guess, but yeah, because isn't moment of inertia also a vector? Yeah, that's true. Okay. I'm going to skip all the way to part C. That's like the important part, the expression for kinetic and potential energies. I got the wrong answer, so let's just see where I went wrong. And maybe you can explain to us where this 7 on 10 comes from. So I say for, this is 1. Oh, I hate this. I want this. Okay, I say for, this is 20, whoa. For 2022, this is question 1, part C. So I say that my kinetic energy is 1/2 mx dot squared. And then does that mean my potential energy will be my regular mgx sine theta plus that moment of inertia?
It's rotational kinetic energy.
It is, hey.
Moment of inertia.
Which is I. Yeah, so I omega squared. And the moment of inertia for a sphere is 2/5?
Yes, I googled this yesterday.
2/5, so that's going to be 5. And then what is it after that?
Radius squared. Yeah. That should be
Whoops.
And then you rewrite your angular rotation as B1R.
Okay. Let's break it really far down. What is our I, our moment of inertia? Cool. And our omega squared is going to be r theta dot.
Yeah. Well, yeah, V on R squared, right?
Sorry.
Where omega is.
My 2's will cancel, and I'll just get a 1/5 mR x dot. Awesome. Oh, it does. Oh my gosh. Oh my gosh. Simple maths. Simple maths. X dot squared. Okay, cool. And then that means that when I do my Lagrangian, I will get 1/2 mx dot squared plus 1/5 mx dot squared minus mgx sine theta. Awesome. And then it's basically the exact same thing as we did before. It then asks you to find the Lagrangian equations, in which case you just do your regular Euler-Lagrange, and then it asks you again for the Legendre transform. And this one works out nicely because they do match up with the Hamiltonian and the Lagrangian. And then using Hamilton's equations again, and then in part H, they end up adding a sheet of ice between the triangular block and the surface that it's on. So now that block can move as well. And that just adds in a second general coordinate. And it asks you again to find the Lagrangian. Are we all good with that though? Like it's literally the exact same thing, but for a different scenario. So are we chill with that? Cool. Is there anything else that was like kind of crazy? No. Okay. If you look at the second question, it talks about a coupled pendula, and it's basically like a swing set with 2 swings, and they're connected to a metal cable at the top instead of like a regular metal bar. The first part says, explain in a few sentences how the swingerling, that whatever this contraption is, works based on your knowledge of forced, damped, and coupled oscillator systems. I said that the metal cable acts as the thing that couples the 2 swings, and it enables the energy transfer between them. I didn't say anything about the damped oscillations. I just said it was like it would arise due to friction. But then I also didn't describe anything to do with forced oscillations because I just assumed no one was on them and you're not adding energy. Do people?
What is forcing oscillations like in I don't know.
Yeah, like, but that's energy transfer coupling, right?
No, but she's forcing it by using the laser swing.
Oh, okay. So if you assume someone is on the swing using, okay, yeah, I guess that works then. For part B, it says you may assume that for this problem that the damping constant gamma is small. In 1 to 2 sentences, suggest the physical sources of damping you would expect in this system. I literally just said the friction in the cable. And then I said air resistance, but that would be tiny. And also, like, there's potential for the swings to go side to side instead of back and forth. That could be another potential damping thing. Do people have anything else to add on to that? No? Okay, cool. This is where it starts to get, they then ask you for like how the frequencies change, blah, blah, blah. When the 2 lengths of the pendula are the same length, that's when you get the most efficient energy transfer between the things. When one of the lengths is super small and you start swinging the other one, that's when you'll get the biggest angle displacement, because obviously really small cable, same amount of energy, it'll start moving more. Another thing that I just wanted to ask you guys about as well is when it says a safety engineer suggests replacing the metal cable and the 2 horizontal sections with a single horizontal bar. And then it says, will the swingerling still work if you do this? I said yes, it will still work because that metal bar is still acting as a coupling thing, but it's going to take longer for the energy to transfer. Would people agree with that? Because like it's still a solid, so you still enable like energy transfer between the 2 swings. It's just going to be a much smaller coupling coefficient. Would people agree with that?
I'd say I assume that the cable would become
Yeah.
the solid, I mean,
Yeah. Yeah. Yeah, I guess. So that's where like that's true. That's true. So yeah.
I think this depends on if the bar is like locked at the end or not, right? If the bar can rotate.
Oh, true that.
It's an Adam question. You can just like word it exactly.
That's true, Adam question. Yeah, that's very true. So yeah. But I also don't know if the point of that question is to get you to like understand that if you tighten that cable, then the coupling coefficient decreases. Whereas if it's super slack, then coupling coefficient is super high and energy transfer is a lot higher. Okay, relax. Because like you could just assume that like a metal bar is just a really tight metal cable.
No.
Okay. Okay.
Sorry, I just someone's example right ahead of.
Oh, right. Yeah, I see. Okay.
The bar has specific pressure.
That's what I was going to say. Yeah. Yeah. So yeah. That's basically all that I'm like kind of confident with. I did also do the relativity question for this year as well, and it's basically the exact same as the calculations we did in our very last in-person lecture, where you just use conservation of energy and conservation of momentum to find mass and velocity. Literally the exact same working. It's an inelastic collision and everything. So yeah. Does anyone have any questions? Yeah. Probably. Wait, 2023? In which question? Question 4? Question 4, part B. The velocity question? Oh, hang on. Wait, let me, maybe. Oh. I actually didn't do this, but let's have a go. Electrons and protons are accelerated through a voltage difference of 10 to the 9 volts. The rest energies of the electron and proton are 0.5 megavolts and 950 mega electron volts. Calculate the relativistic momenta of electrons and protons. Okay. We get given... Yeah, the very last part. I actually missed it. Lol. Okay, so calculate the relativistic momenta of electrons and protons. Relativistic momenta is gamma mv. And I really want to say we get given electron mass and proton mass on our formula sheet.
I say that on my calculator.
Yeah. Calculate the relativistic momenta. We don't have velocities, but we do have rest energies. Wait, am I being silly? Did you guys attempt this question? Because I have a feeling you just convert from mega electron volts to meters per second or something. This is for B, yeah, momentum. We get given the rest energies. Calculate the momenta. And then I'm pretty sure for part 2, to calculate the total energy of these electrons and protons, you use, I don't even know if I'm doing this right. I think that's right. That equation is right. And then you just plug in your momenta into that equation to find the total energy. I think. I will have to get back to you on that unless you guys have already attempted it and just want to chat through it. Have we already attempted it?
Yeah, but I tried to do all in like the
EVs. Oof. Okay, gotcha. Yeah.
You said the masses are equal to 0.5 megaelectron per c squared.
Did you find that off the formula sheet?
No, but you're saying you have a rest energy.
Yep.
It's by both sides by c squared. You put it in the and the c squared.
Hang on, wait. Rest energy is equal to, let's do electron is 0.5. That's 6, right? Mega giga. Yep. Is equal to mc squared per c squared. How do you get per c squared? Wait, but how do we know that? Wait. Electrons and protons are accelerated through that voltage. The rest energies of the electron and proton are that. How do you get per c squared from that? Oh, lol, it is. Forgot about that. Oh, isn't that neat? And then from that you get the M. Plug that M into where? Rearrange this guy. Lol, yeah. Whoopsie. But we still don't.
We know electron mass as well.
Yeah. That's true, yeah. Yes. In that case, you would need that extra formula. I'm not gonna lie, I feel like this was kind of silly, but like I forgot about this, so well done. Because like we already have a mass, we already know the mass. They give us the mass.
Is that the relativistic mass or is it the rest mass?
Rest. Guys, I'm not gonna lie, I'm gonna have to get back to you on that because I'm kind of brain dead.
Then you can just use the rest mass to find velocity. Actually, no.
Yeah, no, it doesn't work. David, do you get people to sign the attendance sheet?
Yeah.
Everyone's done it? Love it. Okay, guys, I'm so sorry. I was a bit brain dead today. I will get those solutions verified and post them on the Discord. As soon as James gets back to me, I'll fix them up and then post them. Oh, and would you look at that? He's emailed me.
If you equate PC squared plus MC squared with MC squared, then the n is the relativistic mass, right?
You're gonna have to say that one more time.
Okay, so the n on this side of this equation is also relativistic mass, right?
It's the rest mass, because this is the rest energy.
Oh, it's not the relativistic.
No.
You want like my sabotage?
I kind of hate relativity, not gonna lie. Oh, I'm so scared. No worries. Thank you for coming.